is about 35% of our power will be generated by hydroelectric by 2050. Obviously, certain regions are going to be much more predominant. I know China is making huge investments in hydroelectric. Certainly Latin America derives a major portion of their electrical power from the hydroelectric grid. And the US is increasing its prospects as well. Europe is a fairly well-established hydroelectric. Certainly in the northern Scandinavian territories, it's quite high. When you move into some of their other areas like France, nuclear obviously takes a much more prominent role in power generation. But it is going to be growing, and it's going to be a significant portion, over 1/3 of our power is anticipated to come from hydroelectric by 2050. In the past decade alone, we've seen an increase of over 25% of installed capacity. So it's a growing market space, and as it grows, we're going to see some more and more problems occurring. One of the first problems we're going to be noticing is that the water volume, the access to usable hydraulic head, is dropping. And this is, as we drop, that's going to have an impact on systems, particularly in the hydroelectric turbine runner blades, where you might experience cavitation. But you'll also see increased flow, and that's going to decrease the power off the grid. An example of this is you can see the water levels in Lake Mead in the United States that feeds the Hoover Dam. That water level has been down 27% in 2016. It's very seasonal, but protracted years of drought have caused that level to drop significantly, and that's having an impact on the Hoover Dam's power production. 27% power reduction at that point. So we have some issues to deal with environmental problems. Some of those are Mother Nature, but some of these are going to be electrochemical issues that we'll talk about now. Now, within the corrosion market space, the National Association of Corrosion Engineers did a study several years ago that looked at various market segments, industrial market segments, and what the cost of corrosion was. And it was identified that hydroelectric is, of the 3 areas that were reviewed in power generation, they looked at fossil power, nuclear power, and hydroelectric. By far the lowest cost of corrosion of the 3 was hydroelectric, but it's still significant. In that instance there, we're seeing corrosion in the maintenance of structures associated with the plant itself. This would be the powerhouse, the dam, and the associated structures. The electrical power plant itself, which would include both the electrical generation area as well as the hydraulic turbine area. The highest cost impact overall is to the water wheels, turbines, and generators. And if you look at the lower table there, you're seeing that's comprising about 25% of the total cost of corrosion. And it's going to be, it's on a weighted factor, it's the highest component of weighted factor cost of corrosion. So that's where we really want to focus. That's one of the high areas of visibility, and also one of the areas that is most prone to corrosion damage. The NACE study, in its summation, the NACE study estimated the cost of corrosion in your operations and maintenance budgets is about $75 million a year for the US. So if you took that $75 million and divided it by the megawatts or gigawatts generated, you could pretty much see what the cost of corrosion is per gigawatt generated, and apply the same numbers to your own region. So there is a significant cost associated with it, and I think it's important that we all recognize and understand that cost, because that's what we're trying to drive down. We're trying to drive down our operational and maintenance budgets to make this system, this power generation process, a more cost-effective and cost-efficient method. Now, when we look at corrosion that's going to be occurring inside the plants themselves, we do have some significant issues. One of the first forms of corrosion that we're going to see is pitting corrosion. Pitting corrosion is another form of corrosion called general corrosion, but it appears in a very localized region. Normally occurs in a specific region which is highly anodic, which means it is more active and more prone to corrosion. One of those issues that will drive that problem is mill scale or oxides on the surface. Those oxides are passive. If those oxides are removed or broken free, a new area of exposed metal is exposed. That becomes the new anode, and pitting corrosion will occur. When pitting corrosion occurs, it occurs in a localized manner, and you can see in this graphic image here the passive layer, which could be oxides, it could be a coating, it could be mill scale. If those oxide layers are removed by erosive flow, by impact, by mechanical stress, you have a small anodic region which is now exposed, and pitting corrosion will be initiated. There is an active ion transfer from the bottom of the pits to the top, And actually, in that lower regions, the pH will be measured significantly lower than the pH at the top of the pit, and that will increase the electrolytic reactivity, which accelerates the corrosion cell. And so pitting corrosion tends to be more localized. It tends to drill down into the steel as opposed to spreading out generally across the surface, and it can lead to pinholes, it can lead to breaks, and it can lead to significant catastrophic failure. It's very difficult to identify it and catch it in time unless you're doing regular inspections, but pitting corrosion is one of the areas that we will be focusing on as restitution correction methodologies. Here's an example of what pitting corrosion looks like. You can see the associated scale on the surface, and where that scale has been removed, the new area has become exposed. That's the anodic region. At the bottom of that anode, you can actually see the hole penetration through, and that's a piece of 9mm plate steel, so that's a significantly reactive pit there. It's probably in the range of about maybe 12 millimeters across, so roughly ½ inch across, and it's about 9 millimeters deep, so about 3/8 of an inch deep, right through the steel. Another form of corrosion that you might see in hydroelectric facilities, not just in the actual operational equipment, but also in the supporting structural steelwork, is crevice corrosion. And this also occurs in a localized region, and it's typically caused by low concentrations of oxygen, which are present in the gaps or crevices. Where are you going to see these gaps and crevices? You'll certainly see them in gasketed flange faces, metal-to-metal fittings. You may also see them in areas where you have stagnant flow, where you don't have, or stagnant flow with no flow conditions. When you have those types of situations occurring, you'll set up very small micro anode cathode cells, and that will also lead to a form of localized corrosion, but it's called crevice corrosion because it typically occurs in these regions which would be noted as crevices. An example of this in a heat exchanger system would be the welded joint between the tube and the tube sheet plate. That small crevice region becomes depleted in oxygen. You'll get active corrosion cells generating in there, where areas are becoming more anodic than cathodic, and that precipitates the corrosion. You may also see it, though, in structural steel reinforcing areas where you have these gaps on riveted structures or skip welded structures. Those gaps become zones, again, of low oxygen concentration. You'll get oxidation occurring and corrosion occurring. As the metal oxidizes and converts to a metal oxide, it expands volumetrically, and that causes stresses and can actually break and pop rivets and cause structural failure. So crevice corrosion is also a problem. And some of these issues that we'll discuss can be addressed by conventional maintenance technologies, but some may require some more advanced technologies. A third form of corrosion that we sometimes see is galvanic corrosion. This is a fairly common form of corrosion. It's typically related to dissimilar metals in contact with one another. These dissimilar metals have differing electromotive potentials, and that electromotive potential drives the corrosion rate. Certain metals are more active, certain metals are more passive. An example would be a pure alloy like gold or platinum or silver. Those are pure alloys or pure metals. They tend to be very cathodic. When you move to the very active anodic region, you're looking at metals like magnesium or zinc, which are highly reactive. If there is a significant differential between the anodic material and the cathodic material, the rate of corrosion will be quite high and quite fast. If the electromotive potential differential between the two metals is quite close, then you'll have slower corrosion rates, but you will still have corrosion because there is a differential in electromotive potentials. In order for this to occur, it normally requires some type of conducting electrolyte. Water is a very convenient one. Obviously, the more acidic or higher ion concentrations you have in the water, the more rapid the rate of corrosion will be. Another area that is required is metal-to-metal contact. So you need to have these differing alloys in direct contact. They can't be separated by any type of dielectric insulator because there is an actual current flow occurring between the anode and the cathode. So in order for galvanic corrosion to occur, you need an anodic metal, you need a cathodic metal, you need a metallic path, which is the metal-to-metal contact, and you need a conducting electrolyte. Now, where would we see this? An example is shown on the screen where you have a hydro runner where they may have done some weld repair. In that region of weld repair, they've used a different alloy, maybe not the same alloy, or the quality of the weld was insufficient, and you've now generated an anodic cathodic region in that weld zone, and that can cause significant issues because the anodic material will fail more rapidly than the cathodic material. Another form of corrosion that we see in hydroelectric facilities is erosion corrosion. This is typically caused by the corrosion mechanism, which is metal's natural state. It wants to revert back to its passive native state. If that's a ferrous-based oxide, you typically look at ferrous oxides. If you're looking at stainless steel, you're looking at chrome oxides. When these oxides form on the surface, they become passive, and these passive layers are actually the metal's own natural method of trying to provide protection. It creates a passivated layer on its surface, which is no longer reactive to the environment. However, that passive layer is very weakly bound to the base metal, and it can be easily washed away. So in turbulent flow regions, which are quite common in hydroelectric facilities, that can wash away that weak oxide layer. If there is any type of sand or silt or suspended solids in the flow, you'll now start to introduce abrasive conditions, which will accelerate that erosion rate. Once that passive oxide layer is removed, now you're going to see an accelerated corrosion occurring in that region where the oxides have been removed. This is a repetitive and a cyclic process that occurs over and over and over. As the oxide layers are removed, the metal is thinning, structural conditions are being reduced, and so we have to be concerned about this. This is most common in your very high turbulent flow application areas. So in a reversing hydro system, a pumped hydro unit, the pumps might see them. You'll certainly see it in the impellers and rudder blades. You'll see it in penstocks. You'll see it in any area where you have high velocity flow. So we want to be concerned about that. When you see the event and how it occurs, it is a progressive approach. In the first image here, you see the weak oxide layer on the surface. You see the flow, which is more laminar in nature now. When that is moving, it's gently across the surface. It's not so aggressive. But if you start to generate some minor areas of attack, these become more, start to create some turbulent flow. And as the turbulent flow accelerates, you start to see an accelerated rate of removal of that weak oxide layer. This progresses over time until eventually the oxide layer is removed, and now I'm starting to remove the base metal because that base metal is repetitively oxidizing, and then that oxide layer is being removed, and the cycle repeats itself over and over again. Eventually, you will see accelerated erosion factors occurring in localized regions, and these are areas of specific damage that we need to be able to address. An example here, a highly eroded pump impeller. This would be, typically you wouldn't see something anywhere near as severe in your hydroelectric facilities unless you were possibly pumping, glacial runoff with extremely high abrasive solids levels in the water flow. But this would be an extreme example. But you will see erosion corrosion occurring in your hydro runners. You'll see erosion corrosion occurring across the wicket gates. You'll see erosion corrosion occurring in your scroll casings around the turbine runners. Another form of corrosion, which is actually a mechanical method of attack, is called cavitation. Cavitation is quite common in hydroelectric facilities. We see this, it's typically caused by low pressure regions which develop in the trailing faces of the turbine runner blades. The air bubbles in the water implode on the surface under extremely high force. Forces several 100,000 psi have been calculated, and they've also established that for microburst periods, extremely high temperatures are also generated across that surface. So those two forces of mechanical stress and thermal stress actually will accelerate the damage to the metal. Once that metal becomes roughened, you start to promote more cavitation, because cavitation likes to operate in rough, irregular surface regions where turbulent flow is more prone. So if you can keep a surface smooth and uniform, that will reduce the effects of cavitation. First and foremost, though, it should be recognized that cavitation is a design issue. It's an issue that should not be counted on as being able to be eliminated by any restorative method. All you're doing is you're repairing the damaged area, but damage will occur again. It's very difficult to eliminate cavitation without impacting or improving your process flow to eliminate those low pressure regions. When you see cavitation occurring on a hydro runner, you'll see it looks like the surface has been frosted or etched. It typically is in fairly localized regions near the trailing edge of the turbine runner blade. on the low pressure side. And these are areas where we want to be able to address, because these are areas of high likelihood of damage occurring in your hydroelectric plants themselves. You can see the level of damage and how it can be severe and actually penetrate through the actual runner blades and cause structural failures. You'll also see throughout the plant what we call general corrosion. This is the exact opposite of pitting corrosion. This is much more uniform across the surface because areas across the metal are becoming anodic and cathodic. They're constantly changing. The rate of attack is much more measured and progressively slow. It tends to occur, and they call it uniform or general corrosion because it does occur uniformly or generally across the entire surface. It's not localized. It is the same corrosion factors are occurring in that you're finding areas which are anodic and cathodic. The anodic region is sacrificing itself, in effect rusting or oxidizing away, while the cathodic area is protected. The issue here in general corrosion or uniform corrosion is an area that is cathodic may become anodic, and an area that is anodic may become cathodic over time. So it is very random across the surface area. The overall effect is the metal loss is relatively slow, and it's easy to assess lifetime. And actually in design factors, if you know what the corrosion rate is, the general corrosion rate, you can design your structures with enough metal to absorb that loss over the lifetime expectancy of the equipment. But when we see general corrosion in hydroelectric facilities, it's mostly attributed to structural steel type applications. Another form of corrosion that we'll see in steel, particularly steel areas, is stress corrosion. And it's called stress corrosion because it's actually a combination of mechanical or thermal stresses, which can be accelerated by certain environmental conditions. One of the most common stress forwards is tensile stresses, where the metal might exceed tensile stresses, and this would be quite common in what you see here is a Francis runner blade, where you have an area of stress corrosion occurring at the regions of weldment. It's important to understand that in any welding application on any metal surface, the heat affected zone of the weld, which is a region roughly 5 centimeters or 2 inches away from the actual weld pool, these regions are more prone to corrosion due to insufficient or improper heat treating. So you'll have areas within the metal grains themselves which are much more prone to corrosion than the actual grain itself. It's the grain boundaries that create the corrosion cells now. So this can be eliminated by effective heat stress relieving, heat pre-treating prior to the weld and then post-treating after the weld, and making sure that the welding itself is done properly by highly skilled individuals using the proper equipment and welding materials. Now there are some traditional engineering and maintenance practices and activities that are commonly used to address some of these forms of corrosion in your plants. Most common one is cavitation repair, and we'll talk about that in some detail here because this is the one that is probably one of the larger issues that you'll see actually in the powerhouse system. The most common cavitation repair technologies are a metal-to-metal process where you're actually repairing the damaged metal with another metal, and that can be accomplished through a weld overlay and grind process. So you're welding on beads of metal onto the damaged area and then grinding everything flush and smooth. Another thing that you can do is simply replace the worn parts. Obviously that has a cost impact and potentially a lead time and scheduling impact, so it may not be the first choice, but it might be an ultimate choice in severe situations. And becoming more common is the utilization of thermal spray technologies. And thermal spray technologies, we'll talk about those in some detail now. Now, your basic weld grind area, you can see there's a fairly extensive rigging required to do this. There's specialized technologies and skill sets that are required. You are generating a somewhat hazardous work environment due to the welding fumes and obviously the fire and flame that might be present. So it's a environmentally and to the worker itself somewhat could be a potential safety hazard. But as far as the actual process itself, if it's done properly and effectively, it can be quite beneficial. If it's done ineffectively or improperly, in other words, they do not provide the proper pre-treating or post-treating of the steel, or they don't use the proper weld materials or welding techniques, or they're unable to grind everything smooth and flush again, they can actually accelerate and make the problem more difficult and more progressive. You can see some of these weld areas and grind areas are quite significant, so it's going to have to be a significant amount of post-treating after the welding as well as pre-treating. Thermal spraying has become more and more common, and thermal spraying is basically it's what's called a high velocity oxygen fuel derived method, where you are actually passing under high velocity airflow either a metal powder or a rod fed into a high velocity airstream. As it passes through an arc, that metal rod or wire or powder is liquefied in that arc flame and is then thrust and forced upon the surface, where it coalesces on the surface as a hard metal. Common metals that are used here are tungsten carbide, chrome carbide, but in some instances, in certain industries, they're doing thermal sprays with ceramic-based materials. But when you're using this system here, it's very important, again, to have the metal surface preheated so that the surface is actually properly wet out by that liquefied metal when it impacts on the surface, and it properly cures on the surface. One of the issues with thermal spray-based systems is they tend to be quite porous, so if there is corrosion occurring, the thermal spray system may not be as effective. It is possible to build these thermal spray systems up in successive layers to several millimeters or fractions of an inch, and they can be quite beneficial in certain highly abrasive applications. Some of the concerns that we have with these metal-to-metal repairs, obviously, is the heat distortion factor. We're concerned about that. That has to be resolved and addressed by pre-treating and post-treating. We're going to be concerned about the heat-affected zone, the actual weld pool and the region directly adjacent to the weld pool. Those are areas that are more prone to corrosion, so we need to be quite confident that weld has been properly inspected and verified as smooth and clean. We do that so we can eliminate the effect of stress corrosion at the welds. And obviously, we're always going to be concerned about worker safety in these areas. If we do not have to introduce flammable or explosive gases, or we don't have to create hazardous or toxic welding fumes, that can be a big benefit as far as improving turnaround time and worker safety. Now, beyond the traditional metal-to-metal repair approach, we want to talk now about some of the polymeric approaches, because polymers are plastics, and plastics are quite resistant to many forms of corrosion. Virtually all of the forms of corrosion that we've discussed so far, pitting corrosion, crevice corrosion, galvanic corrosion, those are all easily addressed by the polymeric materials. Stress corrosion may be more of a problem because, again, you are not addressing the structural aspects of the base metal. All you're doing is just putting a surface enhancement on the surface. And cavitation is another area that can be addressed by polymeric coatings, but you're not eliminating the forces of cavitation. You are reducing the effects. You're allowing the coating itself to be the sacrificial material as opposed to the base metal. So polymers are quite popular because they naturally resist corrosion, and there's a wide range of polymer-based systems. Probably the most common ones that we'll talk about are the epoxy-based materials, which are co-reactive polymers based on a bisphenol A, bisphenol F resin chemistry. Normally, they're an amine-cured structure, so they are what we call chemically co-reactive coatings. When they're mixed together, the two components are mixed together, they start a chemical reaction which will convert that material from a liquid to a solid-based compound in a period of time. They're called thermoset-based polymers because during that reaction process, they actually generate exothermic heat reactions, which actually participates and accelerates the curing process. Now, these polymers, these pure reactive chemistries, can be reinforced with a wide range of inorganic-based materials, glass-based compounds, glass flakes for permeation resistance, ceramic-based materials for wear and abrasion resistance. So all of these types of reinforcements can be blended in whatever ratio is required to achieve the desired performance to provide a wide range of capabilities from corrosion and erosion and abrasion resistance. Another major benefit of polymers, particularly as it relates to the cavitation effect, but also erosion corrosion, is that polymers can resist rapid deformation. They are plastic-based materials, so they are softer and more ductile. So they can absorb some of these loads that are reduced by cavitation. The issue becomes the degree and the rate of cavitation. In extremely high zones of cavitation, it's probably not prudent to use a polymer because the life expectancy of that polymer may not be sufficient to make it to maintenance outages. However, if cavitation is relatively slow and progressive, you may be able to use a polymer-based compound quite successfully to address and repair those zones of cavitation with the understanding that when you come back in on a maintenance cycle of 3 or 5 years later, you may need to do some more touch-up to those areas. Now here's some examples of polymer-based coatings on hydro runners. You can see them being used. You can see them being used on wicket gates for corrosion resistance as well as erosion resistance. You can see them in some of the scroll casings and vanes, turning vanes inside the runners where you're seeing areas of high erosion and high abrasion. These materials could be multi-coat systems. You may be using a paste grade or putty grade material that is used to build up worn regions, in effect using the same technique that is used in the welding approach where you're building it up and then grinding back down. With coating systems, you can build it up, and you can actually build it up and finish it to the desired thickness. If you do require machining or grinding, it's quite easy to grind, and you're not generating heat stress into that base metal because the polymer itself is not going to react that way. So the polymer-based compound gives you more flexibility. Now, there are very defined coating characteristics that we want to see in a hydroelectric coating solution. We want to make sure that the product is able to be applied in confined spaces. And this is a great concern, particularly based on the accident that occurred at the Exelon Power about 6 or 7 years ago out in Colorado. In that instance, there were several workers who were killed in a fire that occurred in a penstock. The fire occurred when a flammable solvent was ignited inside the penstock. And it actually, the workers who were downstream of the fire were able to be evacuated, but the workers who were upstream had nowhere to go, so they moved upstream from that fire to the point where they could no longer climb up the incline. And that's where the rescuers eventually found them in the recovery process. And it was essentially due to the fact that they were bringing flammable-based compounds into a confined space. So whenever you can remove the presence of flame in a confined space, you're obviously going to improve the safety and the work environment. We want to avoid fire, we want to avoid explosion, we certainly want to avoid toxic fumes whenever possible. We want to make sure that the coating system itself has very high adhesion properties, because the most common mode of failure of any coating on the surface is loss of adhesion. It tends to delaminate. Sometimes that loss of adhesion is due to the improper surface preparation or the degree of surface preparation that it was accomplished. But it's very important to ensure that you have very high tensile adhesion forces of your coating system to get a positive bond to the base metal to provide long-term performance. You want to see, whenever possible, you'd like to see cohesive failure as opposed to adhesive failure. And the beautiful thing about epoxies is that they were developed initially as an adhesive compound. That's what they were developed back in the early 30s. And these adhesive compounds develop extremely high tensile strengths so that then when they fail, and all coatings will fail, all materials will fail at a certain stress point, but with these types of coating systems, when they fail cohesively. And that's what you want to see. So the left-hand image is the mode of failure that is desirable in a coating system. It means that the coating's adhesive properties are greater than their cohesive properties. So even if the coating does shear somewhat, there is always a protective layer left on the surface which will provide protection of the base metal. And the nice thing about these epoxy-based coatings is they're easily repaired and restored in place. So it's not a very complicated process. It's effectively dry the area, roughen it by mechanical means, ideally power tool, and then remove any debris and residue left on the surface, and then apply additional coating to the prepared surface area and allow it to cure. The curing process can take some time. It can take anywhere from several hours to a day or so, depending upon the temperature in the application area. We want to make sure that the product has good erosion resistance, because hydroelectric systems are exposed to tremendous amounts of erosive flow. High volumes of water moving through confined spaces, basically going from a laminar flow to a radial flow type of application, so there's going to be directional changes, and that's going to accelerate the rate of erosion. So we want to make sure the material has good hardness. High hardness can be imparted not just by the epoxy itself, but also by the reinforcement. So when we start to incorporate some of the harder reinforcements like the silicon carbides or aluminum oxides, the material now develops a Mohs hardness that is approaching the Mohs hardness of diamonds. Ceramics that are used in many of these coating systems can be as high as 9.8 on a scale of 10. And those types of materials will provide you very good erosion resistance, and if there are particulates in the flow, they will provide good abrasion resistance to keep the polymer in place. Many of these polymeric-based coatings can also be applied in a very smooth and low coefficient of friction surface, and that's also going to improve performance over time. So being able to do rebuilding and wearing in these areas which are subjected to erosion are important. We want to focus on cavitation ability, the cavitation resistance capability. And the benefits of the polymer-based compounds, as I said earlier, is their ductility and flexibility. They can absorb the rapid deformation impact of the cavitating air bubble, and they're flexible over time. So they will give you good performance. They're not going to, again, eliminate cavitation, but they can be used to repair zones of cavitation, to prevent accelerated cavitation in those areas, but you will more than likely have to come back there and do repetitive maintenance within your maintenance cycles. So when you start to see these zones of cavitation, these need to be addressed and repaired. And finally, stress corrosion, and this is an issue that comes up. There's both flexural stresses and tensile stresses that are going to be present in many of your hydro runners. When you see distortion of the metal, that's indicating there's significant tensile or flexural strains on that base metal. As you accelerate those strains, the zones of weldments become more prone to cracking, and those areas need to be protected. So these are some characteristics that we want to see in a coating system. The ability to resist flexural stress. That means they should either be, you can have materials that are low modulus, they become more flexible and more ductile, and as long as they can resist the erosive flow forces, they're going to be beneficial. If they're so soft that they cannot resist the erosive forces and they are scoured away, nothing is gained. Now, excuse me, when we're looking at considerations, what do we want to consider when we're going to introduce a polymeric coating into your hydroelectric structures? There are certain things that we recommend that be followed. And the first one is an inspection. You want to make sure that the coating is suitable for the type of application that you're anticipating. Sometimes a coating is not going to be practical. In those instances, you may need to go rely back on the base metal repair or spare parts replacement or even thermal spray applications. So inspection is an important process of it. You want to look at the base surface that you're going to be reviewing and addressing and identify what the conditions of damage are so you can make the proper selection of materials and steps to go forward and develop the process. The material selection may incorporate rebuilding materials that are used to resurface pitted and worn regions. They may then also require a top coat system which is smoother and more low friction, that has better hydrodynamic characteristics that will improve the hydraulic flow across the surface and reduce the forces of cavitation. So taking a material that is worn and pitted and rebuilding it using these fairing compounds to smooth the surfaces and fill the pits and build the metal back to its original dimensional clearances, and then application of top coat systems on them to smooth them out and give them better performance. Now, in order to address these applications, surface preparation is extremely important. And that is probably going to be, in my experience, it'll probably be the most expensive cost component of any polymeric coating application is the surface preparation and application. But this is an area where you do not want to cut corners. This is an area you want to make sure that you follow the manufacturer's instructions, that you provide the proper profile for mechanical adhesion, that you provide the proper environmental conditions for the coatings to react properly and cure within the stated time frames, that you use the materials in the proper sequence, that you're rebuilding and resurfacing before your top coating, and that when you are applying multiple coat systems that you are meeting what's known as the overcoat window, which allows you to apply successive coats one over another without any additional surface preparation requirements. If you were to exceed one of those overcoat windows, which are time and temperature dependent, then that would require you to re-roughen the surface, bringing back in your mechanical profiling process. So the process itself involves a fairly extensive investment in time and money. The largest investment in time and money of any polymeric coating application will be addressed by surface preparation and application. My experience says it's usually somewhere between 75 and 80% of the cost of the job is surface preparation and application. But when done properly and done successfully, the coating systems then have the best opportunity to perform, and they become quite economical because you can affect these repairs quite quickly in a matter of days as opposed to a matter of weeks with some of the more traditional methods. and there's nowhere near the amount of cost involved as far as rigging and heat stress relieving, both pre and post heat stress relieving. So it's a more effective approach. So we look at the coating systems as a beneficial ability to provide erosion resistance, corrosion resistance, and corrosion resistance to pitting corrosion, galvanic corrosion, crevice corrosion, erosion corrosion, cavitation, and by protecting the weld regions where you do have the potential for stress corrosion, we can eliminate environmental effects that can accelerate that stress corrosion cracking. Now, when we consider where coatings can be used within hydroelectric plants, they're used in many regions, not just in the powerhouse though. They're used in the scroll cases and the wicket gates. So this is areas where you're going to see high erosion corrosion forces. You may see cavitation on the backside of the wicket gates. These are areas where you're going to see, if there is suspended solids, areas of high abrasion as well. The turbine bulbs themselves, the radial gates or tainter gates, these need to be protected. These need to be associated with your dam structure as your relief valve basically for your dam. Both the upstream side and the downstream side can be protected with these types of polymeric coatings for extended run times and long life. Penstocks themselves, both riveted as well as welded pipe construction. These types of systems, long runs of pipe, typically at some angled pitch. There's going to be high velocity flow. Again, you're going to have corrosion occurring here. There may be isolation valves intermittently placed along these penstocks where you also have to provide corrosion protection inside the penstock to the valve itself. The actual dams themselves, sometimes you're dealing with the nosings of the dam, particularly in the northern climates where they have icing structures and what we call frazzle ice. Frazzle ice will actually act like an abrasive compound and will wear away the weak concrete layer until it exposes the aggregate, and the aggregate will start to pop out. When the aggregate starts to pop out, now the underlying rebar can be impacted, and then you're going to see accelerated spalling corrosion and more structural damage. So it's important whenever possible to provide coating systems on the upstream areas where frazzle ice damage is prone to provide a protective layer on top of the concrete to prevent that type of damage from occurring. Bar screens and some of the intake structures, trash racks, these are large core screens at the upstream side of the penstock. These are designed to filter out large floating objects that might get inside the penstocks and the turbines and cause mechanical damage, logs, boats, things like that that might be floating in the riverine areas. The actual runners themselves need to be protected, and we're talking about not just the Francis wheel that you see here, but also Kaplan and Pelton style wheels. Wherever you're going to see erosion, corrosion, and or cavitation, these are areas where you can apply these types of polymeric coatings and get good performance life for a longer period of time. And finally, we look at the actual spillway structures themselves. Above the spillway, you see the tainter gate or the radial gate. When those gates are opened due to the high dam levels, that flow of water passes very quickly across that surface and it causes erosive damage to the concrete. Concrete is chosen not because of its abrasion resistance or erosion resistance. It's chosen based on its cost and its structural strength under compressive loads when it's been reinforced. It's not a highly abrasion-resistant material. So in those instances, it might be beneficial to apply a more erosion or abrasion-resistant coating on top of the concrete, particularly in the high-flow regions. As you move up, if you move up the walls where the flow is less pronounced or the velocity and impact damage is less pronounced, then you don't need to use a coating. But in this instance here, coatings have been applied across the spillway floor as well as about 1 meter to 1.5 meters up the walls where the flow is highest. So these are areas that coatings are used quite commonly in hydroelectric systems, and they're used with a high degree of success. And to review them, I'd say that the areas associated with power production would be your bar screens or your core screening systems, your intake structures, your penstocks, any isolation valves as you move down into the actual powerhouse itself, the scroll case surrounding the turbine runners, any wicket gates or turning vanes that are used to convert that tangential flow into radial flow conditions, the actual turbine runners themselves, the turbine runners, the draft tubes below the turbine runners. Normally there may be a cavitation ring below that if it's a Francis or Kaplan wheel design. And then you'll obviously see corrosion or erosion occurring in the dam structures, in the spillway areas, on the tainter gates, and any of those areas. So Polymeric coatings can be used broadly across these areas, giving you a very good tool to fight these effects of erosion corrosion. You also have the conventional methods of metal replacement, metal repair, and thermal spray systems. So there is a body of knowledge and a body of experience that exists in utilization of these maintenance technologies to address the degradation effects of environmental corrosion that occurs in your hydroelectric facilities. And we think that over time, polymeric-based coatings will become more prominent because of their ability to perform under highly erosive conditions and their cost effectiveness. And that will be the conclusion of the webinar, and I'm more than happy to address any questions that you might have at this time. We'll stay online for a few more minutes to make sure that everybody who was listening in, if they have any questions, please feel free. This is also being recorded, so if you've signed up for this webinar, you will be able to access the recording and review it, or forward on the information to other people to review the webinar. Not seeing a lot of questions at this point. Okay, we have a question here coming in. That's the question is are there any long-term studies which compare the costs of polymers versus traditional methods? Long-term studies would be defined, the longest term study I'm aware of, it was one that was done by the U.S. Army Corps of Engineers, where they looked at weld repair and polymeric coatings. This was a study that was done back in the mid-1990s, and that report indicated that the polymer-based systems are quite cost-effective, but you need to be selective in where you use them. You shouldn't be inclined to use them in all applications, and that's why it's very important, if you are considering a polymer-based coating system, is to make sure that the manufacturer's representative, who is the subject matter expert on the coating system, is able to inspect the area or get a report on the conditions so he can make sure that his product is appropriate. We want to make sure that anybody who's recommending any of these polymer-based coatings understands the limitations. They're not, by any stretch of the means, a placebo able to address any problem. We're going to have to take a look at what the conditions are. But that study was done by the Army Corps of Engineers. If you have any interest in that report, I'll be happy to send you a link to it. I believe you can get in touch with me. My email address is bowdits@chesterton.com. So if you have any questions on these issues, please send them in to me. I can forward on that report for the Army Corps of Engineers. EPRI, I'm not sure if EPRI has done a study in the past 10 years. I'm not a member of EPRI, so I don't see the EPRI reports, but I would certainly wouldn't dispute that EPRI should be involved in this. The Electric Power Research Institute has been around a long time. A couple of good friends are still on the committee there, and they may very well have done a study on hydro systems and polymers. I'm not familiar with the EPRI one. Thank you for the question, Tony, though. Well, folks, if there are no more questions, I'll release you to the rest of your day, and I want to thank you. Oh, we do have a question. Is there? Oh, thanks very much. All right, then I'm going to conclude this webinar today. It is recorded, so you will have access to this. And I want to thank you for your time and attention today. And hopefully we'll see you out there in the world. Bye-bye.